All right, and thank you all for being here, and for the organizers, Amy, the tech guys, and everybody, and CIBC. It's been wonderful. So very, very happy to be here. And I'll talk about the celestial mechanics of attention mechanisms. So we're going to go a little traditional ML here. So I'm traditional, I mean like 3 years ago. Because I don't know you, but this drives me crazy. ChatGPT talks one word at a time. Are we all okay with this? This is so messed up, right? Like if you want to make it write something amazing, the most amazing story or essay, it's not going to do it. It's just going to give you the first word, the. And if you want a second word, you just have to bring the first word and put it in the input and then get the second word and then do that repeat. And that's how it talks. That drives me crazy. You know why it drives me crazy? Because we had that a long time ago. Like 10 years ago, we had autocomplete. And autocomplete is basically the same concept as ChatGPT. You give it a text, you're writing your text message, and you say, hello, how are? And it just gives you not just one, 3 words. So we had a chatbot along. Like scientists were scrambling their heads 10 years ago to see how do we make a chatbot? We had a chatbot. It was just not very good. I don't know if you've ever tried to type using the middle button. I tried, and it goes, hello, how are you feeling this weekend? Your kind wishes for a wonderful weekend with your kindness and happiness for you, blah, 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 blah. It doesn't speak very well, but it speaks, right? And if you look at it, this is not so terrible, because if you look at every 4 or 5 words together, they make sense, right? Like, hello, how are you feeling? And happiness for you. It just doesn't carry context for a long time. But it's just like Dory talking from Finding Nemo, right? It just has a really low attention span, and it just switches topics, but it talks, right? And so the question is, how do we go from that all the way to ChatGPT, where you can ask it something like, tell me about Nietzsche's philosophy applied to AI, and it comes up with an amazing essay. How do we go from there to there? Well, one thing is the context window, right? Like when it comes up with the word kindness there, it only has the capacity to look for like maybe 4 or 5 words. It's an RNN. It cannot go too far. The first word has no input on the last word there. The word hello has no input. Whereas here, if you want to put the word algorithms, you have a huge context window. It can remember a lot of stuff before. And not only that, because that's a lot of stuff to remember, it knows where to look. Like if it has to it's going to put the word algorithms, it knows what words are similar and where it should pay more attention. So that's the attention mechanism. It's not biased on the recent stuff you said. Is biased on like anything that looks a lot like what you're saying right now. So similarity is a very important concept. And attention is what did it. So I would say that if ChatGPT speaks is, well, because we have more computers, bigger neural networks, more data, but the conceptual advancement was the attention mechanism, came out in this paper. Attention is all you need. That introduced the transformer. And I would say that if the ChatGPT is the DeLorean, then attention is the flux capacitor, the one that makes it time travel. I realize I am aging myself with this reference, so for the younger crowd, if ChatGPT is Iron Man, then the arc reactor is the attention mechanism, the one that makes the suit work. Okay? And so today, I'm just going to tell you about that. So basically, large language models stand on top of the attention mechanism. They work because they have attention. And attention works because of similarity, because you pay attention to the stuff that's similar to what you're saying right now. And similarity stands on top of embeddings. So let's see all these things. And they're all there in the original diagram of a transformer. Embeddings are red, attention is the yellow, and the blue is the WhatsApp autocomplete that generates the next word in the sentence, right? So first, let me tell you how I see embeddings. And embeddings, to me, are the most amazing thing in machine learning, not just in text, but in images and video, because it's really where the rubber meets the road, right? Like this is really where you go from human speak to computer speak. Humans, we speak in words. Computers have no clue what a word is. So they just handle numbers. And you need a bridge, like you need a really good bridge between words and numbers, something that sends words to numbers in the best possible way. And that's an embedding. So I don't like to see a lot of numbers together. I just like to see things flying around in space or in the plane. Here I have a grid with a bunch of words. with avenues and streets, horizontal and vertical coordinates, like this, for example. Tennis is at 1.5 because if you go 1 horizontal, 5 vertical, you get to the tennis ball. So I have the first quiz in the morning since we're all waking up. And the quiz says, where would you put the word apple? Would you put it at A, at B, or at C? So put up your hand if A, put up your hand if B, put up your hand if C. Yes, you all did very well. You would put it in C. Why would you put it in C? Who can help me? Is where the fruits are, right? Fruits should stick together, right? At the very least, is the least I can ask of an embedding, that it puts fruits with fruits, right? So it puts it in C in coordinate 5, 5. So that's the least we can ask of an embedding, is that it puts similar words to similar numbers. Now, this one sends things to 2 numbers, and computers can fit a lot more than 2 numbers, right? So an embedding is basically a list of numbers, a vector of thousands of numbers. I've seen them all the way to 4,096. The normal ones, 1,000, 1,024, 700, something, are the ones you would see on language models. But basically, think of 1,000 words that describe 1,000 numbers that describe each word. And I like to see them as properties of it. So it could be color, it could be size. The computer knows stuff that we don't, so it's hard to see what these properties are. But if you imagine that there's 1,000 properties per word, and each one is measured with numbers, then it makes sense that similar words are sent to similar numbers, because the numbers for apple are similar to the numbers for pear, because they're a description of it, right? So that's an embedding. So you did very well in quiz 1. We have now a quiz 2. And the quiz 2 says the following. I have an embedding here, where in the top left, I have a strawberry and an orange. In the bottom, I have a smartphone and the Windows logo, okay? And now you're gonna help me. You're gonna say top right or bottom left, top left or bottom right. And it's gonna be rapid fire. So you can just yell top left or bottom right. Where would a cherry go? Good job, top left. Where would Android go? Yeah, everybody's super awake. Bottom right. Where would laptop go? Bottom right. Where would banana go? Top left. Great. Where would Apple go? Both in the middle. It's hard to tell, right? Because we don't know if I'm talking about a fruit or if I'm talking about the company, and we're not going to know. Like, there's no embedding that good that will know this. Even if somebody comes up with the best embedding in the world, they're not going to know where to put an apple, because that's not a problem of the embedding or of the models or the computer. That's the problem with the language. That's a bottleneck in the language. Language is ambiguous. And so we got to go a little far. We got a problem. And we have to find a solution. And the solution is not going to be an embedding. It's going to be somewhere else. And that's what attention does. The attention helps us know where to put that ambiguous apple, okay? So here's attention, blah, blah, formula. But the idea is that I like to see attention as basically using context. Because if I stand in front of you and I say apple, then you would expect me to at least say more stuff to see what I'm talking about, to give some kind of context. And so help me out. If I say, please buy an apple and an orange, what am I talking about? The fruit or the company? Good job, the fruit. If I say Apple unveiled a new phone, what am I talking about? Fruit or company? Good job, company. Okay, and now help me out. What word gave it away? What word gave you the idea that I'm talking about a fruit in the first one and a company on the second one? Say that again? An apple. An apple? Oh, yeah, apple works. Well, there's one in per sentence, right? I heard it somewhere. Orange did it, right? And phone. Because please didn't do it. I could say, please buy an Apple Watch or something. Or the one that gave it away is orange and phone, right? So thank you for the answer. And so we're going to use those words to pull our apple around in the embedding. And literally, it's that. So if I have my embedding, and my orange is on top, and my phone is on the bottom, and the ambiguous apple is in the middle, what the attention mechanism does, literally pulls it. So orange pulls apple in the sense that it just pulls it a tiny amount towards it, and it modifies the embedding. So the embedding of apple is not those coordinates at the middle, it's the coordinates of the moved apple. So you're modifying the embedding based on context. And the same thing, if I have phone, apple embedded in phone, then the word phone pulls the apple down, and I'm getting closer to phone. This happens very little, but it happens many times. And so basically, if you think of words flying in space and context meanings, gravity, where words pull each other, then that's pretty much the attention mechanism. Now, we're in a bit of trouble here because we knew as humans that the magic word there is orange, but the computer doesn't really know, right? For the computer, all the words should be pulling because it just doesn't have that logic that we have. So it seems like we're in a bit of a pickle because now words are going to be pulling around all over, and we're going to have a huge mess of words pulling each other. So what can we do? Well, we are in luck because embeddings happen to put similar words in close positions. So apple and orange are close by. And so it's kind of like magnets. Magnets that are close by attract each other more. If they're far away, they don't. Or like planets, right? Like gravity, right? Like planets that are close by attract each other more. If they're far away, they don't attract each other. So if we make sure that the formula includes the fact that close words pull each other more, we're good. So apple and orange have a strong gravitational pull, whereas apple and bi don't have a strong gravitational pull. So apple and orange pull each other a lot. Apple and bi don't, barely pull each other. And this is all in the formula. For those who like formula, this is exactly what this formula says, because KQ is the similarity. The higher it is, the more the pull. And the softmax makes sure things move in a line. The softmax makes sure the coefficients add to 1, and that's exactly the same as moving in a line. So if you like formulas, that's exactly that. And I like to see it as gravitation, right? Because the Earth and the Moon are close by. They attract each other a lot. The Earth and Saturn, not so much because they're far away, okay? So pretty much, that's how I like to see it. If I've been talking about fruits for an hour, and I say apple, now you know I probably mean the fruit, because there's a very strong galaxy here of fruits. Computers are there, sports are over there. But if I'm talking about fruits, I got a galaxy here, and when I say apple, it just gets pulled towards the fruits, and it's very likely that I'm talking about a fruit. Okay? So far, so good. Any questions? Here, stop me if anything doesn't make sense. All right. So I've been using distance a lot, but I'm kind of lying to you because distance is not the best measure. It's actually similarity. The concept of two words being similar or different is huge for language models. And the better this concept is, the better everything is. So I've been using distance in the sense that, orange and pear are close, Android and orange are far. But I want a number that's high when two things are similar, and low when two things are not similar. So there's 3 ways to do it. One, as I said, is distance. If you're far away, you're not similar. If you're close by, you are similar. That's the worst one. Angle is better. So actually, you do an angle with the origin. And the bigger the angle, the farther away you are. If you have a big angle like orange and like pear and Android, you are far away. And if you have a small angle, you're close by and you're similar. That's the second way. Third way is the dot product, which is more numerical. You just take the first coordinate of both numbers, the 7 and the 6, multiply them, and then the second coordinate, so the horizontal coordinate and the vertical coordinate, and you add them. That's kind of where the dot product, so I don't like to see the dot product as dot product. I like to call it the Tinder similarity. What's the Tinder similarity? Let's say you want to see if 2 people are similar or not, and they fill out a questionnaire which says, do you like long walks on the beach? Do you like pineapple on pizza? And do you think dogs are better than cats? And everybody answers their question. And so these 2 people, I want to see how similar they are to see if I recommend them on Tinder. Well, they both answered that they like long walks on the beach, they don't like pineapple on pizza, and they disagree on dogs better than cats. So how similar are these people? Well, I'm just going to put a -1 for no and a 1 for yes. and then just multiply their answers. Why multiply? Because if I have two ones, it multiplies to 1. If I have two negative ones, it multiplies to 1. That's good. Checks if it's the same number or not. And if they're different, then the product is -1. So that's why dot product works, because when you multiply the coordinates, you get a big number if the things are similar, a small number, they're different, because it could be negative and positive, okay? So, and then you add them. So that's dot product. Turns out that, yeah, distance is not a great way to measure. Angle and dot product are good, and they're actually very similar. They don't look very similar, but when you look at the angle between things and the dot product, you're doing pretty much the same operation up to a scalar. And if you remember from high school, this formula, cosine of A minus B is cosine cos B plus sine A sine B. The bottom one is the dot product, the top one is the cosine of the angle. So we're doing the same thing. If you, sometimes I forget and I do dot product and then I switch to angle and then I switch to dot product. Forgive me if I do that, but it's because they're very similar. But here's a question. If we can talk about distance between words, why do we bother talking about the angle? How nerd are we to like start doing like the angle between something? Who can tell me why? Any ideas? Yes?
Because we got challenges with distance.
There are challenges with distance that are... And what?
More the number of dimensions.
That's true. Dimensions, with you have a lot of dimensions, it's more expensive to calculate the distance. That is very true. Thank you. The cosine is bounded. Yeah, it's between -1 and 1. Distance can be huge. Great, great answers. I'm learning a lot of stuff. Yes, you and then you.
Is it more efficient because it can be pre-calculated for all the...
You can, I think it's more efficient. Yeah, probably. It can be, yeah. Because you don't have to square stuff. Like distance, you have to take squares and square roots. Yeah. And you? Say that again? The type of variable.
Yeah, for example, if height is different, perfect. So if height is different in one case, and in the other case, another variable is different, the distance might end up in the same thing, but the angle would be different.
Oh, that's interesting. Okay. Yeah, I never thought of that. That's pretty good. So thank you. Great reasons. Great reasons. I have a slightly different one. They all work well. I have a question. Is there anywhere else other than embeddings where we use angles instead of distance? Any place in the world where you would do that? I'm going to give you a hint. Any place in the world where you would do that? In the world, right? We never do distances like this. We do angle distance. If I want to fly from somewhere to somewhere else, I don't open a hole through the earth and calculate the straight distance. Straight distance means nothing in the world. We use straight distances when we're close by, but it's really an angle. We just pretend it's straight because it's close. But the distance is between two places in the world is given by the angle with the center of the earth. So angle distance is not that crazy, right? It happens a lot. And why do we do it in embeddings? Because embeddings, this is an exaggeration. Embeddings are not circular, but they behave more like spheres than they behave like the universe. If you look at an embedding, obviously there's a lot of spikes, there's a lot of mountains and valleys. It's not going to be as nice and spherical like this. But if you look at an embedding by standing in the center and looking at words around you and looking at angles, is better than if you look at it from far away and start measuring distances. And it's because of phenomena, and it's better to take angles. And it's because of phenomena like this, for example. You can have a word, this doesn't happen in every embedding, but I've seen it a lot. You have a word like bad, and you want to have a word like atrocious, which is an exaggeration of bad. They point in the same direction. They look close from here, like two stars that are far away, but they really look like they make the same angle with you. And it's better to look at them as the angle than how far away they are. Look at how far they are, but they form a small angle. So that's why we want to look at angles and dot product instead of distance. So we have that the words are flying in the universe, and that they attract each other based on gravity. The question is, are we done? And we're not even close to done, because things can get pretty complicated. In particular, I've been talking about similarity But similarity is a lot more complicated than it seems. And that's why we introduced something called the keys and queries matrices. They're going to help us find the perfect gravitational formula for words. I'm including matrices. I don't know how you feel about matrices, if you have good memories from them back in high school or bad memories. But the way matrices are seen is as arrays of numbers. I'm not a huge fan of calling them arrays of numbers because to me that's like looking at a book as an array of letters. Matrix is not, a book has stories that are told with these letters. They're not just random letters. It's in the same way, matrices tell a beautiful story. And one of the stories that matrices tell that I love are linear transformations, okay? What's a linear transformation? Let's say I have an image. I'm going to do them in 2 dimensions, but you can imagine this in 3 or in more. What can I do with this image of a dog? Well, I can rotate it. I can stretch it in different directions. I can also do something else, which is like I put the book on the table and I push the top. So that's called a shear. These are all matrices, okay? 2 by 2 matrices. And if I combine all these in any way I want, I have what's called a linear combination, a linear transformation. It takes squares and turns it into parallelograms, okay? Whenever you have a square goes to a parallelogram, you have a linear transformation. If a square goes to a circle, that's not a linear transformation. But a parallelogram, you get a linear transformation. And we're going to apply linear transformations to our embeddings to make them better. Now, here's a question. If I have a perfectly good embedding where Android is all the way there, pear and orange are all the way down here, why on earth would I want to mess with that and get something like this? Why would I ever want to do this? Seems like that one's pretty good. Well, it turns out that I do want to mess around with them because embeddings have a lot of weaknesses that can be fixed, okay? 3 reasons. I'm going to give you 3 reasons why you want to mess with embeddings. And the first one is that not all dimensions imply similarity in the same way. So, quiz number 3. This one's more conceptual, so it comes with, you have to explain your work. I'm going to give you 3 embeddings, and this embedding is on the horizontal, I have size, so the more to the right that you are, the bigger. And then on the vertical, I have animalness, so you have non-animals on the bottom and animals on the top. And I'm going to give you 3 embeddings. And if you can tell me which one do you like more of these 3, just out of the blue, like interpret it however you want it, which one of these 3 do you think is the better embedding for similarity? And all of them work, by the way, if you have a good argument. So I have my favorite, but you can tell me which one you prefer. Who said 2? Good job. I like 2 as well. Why do you want to share why, or somebody want to share why?
Classification, like animals, species.
Yeah, it kind of has the animals together. Makes sense. Yeah, I like that. Any other thoughts? Anybody like a different one?
I like 3.
You like 3? Okay.
There's a very distinct thing between something that's an animal or not an animal, but there's a lot more variation in size.
That is true. Yeah. So I think the question is, do you want to have variation in size or in animalness? And I think it could be the third, it could be the first, it could be the second, depending on how you want to say 2 things are similar. Do you want to say 2 things are similar, they're both animals, or they're the same size? If you're packing stuff in a ship, you probably want size to be the similarity. I'm going to sort of guess that if you're talking, maybe it's more likely that if you bring up an animal, you bring up another animal as opposed to bringing up something of the same size. So in my head for talking would be this one, but again, all of them work if you have the right argument. But do you see, like, I think the elephant and the bunny are closer when it comes to similarity, when it comes to talking, right? One word is more likely to make the other one appear as opposed to truck. So therefore, we go from this to this. That's a linear transformation. What I did is I multiplied the size by a small number, maybe 0.3 or something. I multiply the size by a small number, then it speaks less loud. This also works in Tinder similarity, right? If I tell you that 2 people have the same opinion on long walks on the beach, on pineapple on pizza, but they have different thoughts on marriage and kids, Would you set them up on a date? No, right? But they matched on 2 out of 3 questions. Sounds like they didn't match on the important question, right? So questions are worth differently, just like size in the embedding and animalness. What I would do is I multiply the third one by like 10 to really amplify that score, and the other 2 by small numbers. So if you go through your embedding and multiply some entries by big numbers and small numbers based on how important they are for similarity, then you have transformed your embedding in a way that makes similarity work better. So are we clear? That was the first reason. We have 2 more, and then we're done. The second reason why you want to mess with your embeddings is because sometimes you want to combine dimensions. So I'm going to give you an example. Let's say that I have 2 very good students, Aisha and Beto, and they have to fill in a drop-down menu of what's their favorite subject in school. Now, Aisha loves math. Math is her favorite subject, and Beto's favorite subject is physics, okay? And this is the embedding. The embedding is if math is your favorite subject, you get a 1, otherwise you get a 0. If physics is your favorite subject, you get a 1 vertical, otherwise a 0. And you're going to tell me now, among these 3, which one do you like more and why? I hear 2. Yeah? You want to share a reason? STEM, right? It seems like 2 works, right? Like, of course, there's an argument for everything, but in my head, these 2 students are more similar. This embedding is very unforgiving, right? Because if you like math and physics is a close second, and then suddenly you like physics a little more, you made a small change, yet the embedding sent you from this corner to that corner. That's not good. So we got to make the embedding a little less unforgiving, right? And so 2 seems to be the best one. Again, arguments work for all of them. But in this case, let's say that we want to make the students closer to each other. And so we just, what we're going to do is the following. If your score for math is 1 and your score for physics is 0, I'm going to say, you know what? I'm going to give you 0.5. If you like math, that's a 1 for math, I'm going to add 0.5 to your physics score just to make it a little more, you know, closer. And so that means I'm moving her from the 1, 0 to 1.5. And then I'm doing the same thing. If you like physics, I'm going to add 0.5 to your score in math, thus moving the kid towards the right. And now they're closer. So what I did to this embedding is I took the math edge and added 50% of the physics edge. So this is my new math plus a little bit of physics. I took the physics one and added 50% of math. So my new one is this one. And then the rest follows. So I transform my embedding from that into that, which keeps the 2 students a little closer, right? So in other words, sometimes I can, reason number 1 is some dimensions speak louder than others, and I have to multiply them by numbers. Reason number 2 is sometimes 2 of them speak louder when they put together than when they're separate. Those are the normal ones. The weird one is this one. The pool doesn't have to be symmetric. That's a very strange one, because so far we've said if 2 words are similar, they pull each other the same amount. That doesn't need to happen. Actually, many times 1 word pulls the other one way more than the other one pulls the one. Like with planets, right? Like, I mean, the force is the same, but Jupiter just pulls more, a little moon more than the other way around. So the same thing happens with words, except the opposite is the small word, the one that pulls more. And you're going to help me out. I'm going to give you 2 words. Tell me which one pulls the other one more into the conversation. Fisherman and net. Fisherman pulls more, right? Correct. Why would you think fisherman pulls more? Agency, yeah, exactly. And there's more to a net, right? Like there's a lot of kinds of nets. So fisherman pulls more than net, because if I'm talking about a fisherman, I'm likely to bring up a net. Whereas if I'm talking about a net, I could be talking about the internet or a tennis net or a network of something. It's not so likely I'm going to talk about a fisherman. Maybe, but it's a different pool, right? Think about this. There's a movie called The Fisherman. I assure you there's a net in that movie. There's a movie called The Net. Pretty sure there's no fisherman in that movie, right? So pulling is not attraction is not symmetric. Like in Tinder, right? Like you can't just be like, well, these two people answer the exact same questions in the exact same way. They're very similar. Unfortunately, that's not how the world works, right? What the way it works is you have a bunch of features that are the stuff you want on a couple. You have a bunch of features that are the things you offer, and you can't just match line by line like in a normal dot product. You have to match what you want, what the other person offers. If that's big, there's attraction in this direction. And then what this person wants with what this one offers, and that's the attraction in the other direction. And there's no guarantee that those two edges have the same thickness, right? Could be vastly different. Same thing happens with words. So the word fisherman has a lot of properties that pull other words and a lot of properties that make it get pulled. And you got to match, oh, sorry about that. And you got to match these green ones with the orange ones. The ones that pull are called the keys. The ones that get pulled are called the queries. Okay, so you got to match keys with queries, not row by row like the normal dot product. Okay, but that's unfortunate because if we transform our embedding, then we can't have two different forces because it's based on distance. So we don't need one embedding, we need two embeddings. So this is going to look a little contrived, but the idea is that you make one embedding for the keys, the pullers, one for the queries, and when you put them together, you can mess around so that if you want to find out how much fisherman pulls net, you look at the fisherman key and the query net, and if you want to see how much net pulls fisherman, you look at the key net and the query fisherman, and that's how you do it. Okay, I know this looks a little contrived. I have a numerical example. It's my favorite example, and that's me. It's not my favorite because I'm there, but because Taylor Swift is there, and I'm a huge fan of Taylor Swift. I'm a big Swiftie, I have to admit. Tell me something. Who's more likely to pull the other one into a conversation? Taylor Swift pulling me or me pulling her? Be honest, I can take it. So probably I pull her into conversations more than she pulls me into conversations, because if I'm such a Swiftie and I'm always talking about Taylor Swift, and two people are talking about me, they'll be like, where's Luis? Oh, he's probably at the Taylor Swift concert. So I pull her into conversations about me. The other thing may not happen so much. If two people are talking about Taylor Swift anywhere in the world, I don't get pulled into that conversation. I should probably stick where I am, right? So there's a strong pull in one direction and a weak pull in the other direction, right? And she's the more popular word. She would be Jupiter, I'm the little moon, but I'm the one who pulls, right? The less common word is the one that pulls more, and the big one is the one that gets pulled. So let's put some numbers. We have an embedding, and my embedding, the horizontal axis is how much you like pop music, and the vertical is how much you make pop music. So one of those is the puller, one of those is the pulled. And this is our embedding. So where am I? Well, I like pop music, but I don't make it, so I'm at 1, 0. Like pop music, don't make pop music. She's at 1, 1, because likes pop music, makes pop music, so she's all the way there. And if we're going to take the dot product, we would take 1 times 1 plus 0 times 1, but that makes no sense, because the fact that we both like pop music doesn't mean we get pulled into the conversations, right? Like, that makes no sense. Dot product does not do it. And what you want to do is one feature is the key and which one is the query. Who can help me out? Which one is the key, the puller, and which one is the query, the pulled? The key? What of the two features is the one that pulls others into conversation? Likes pop music. Good job, yeah. And then makes pop music is the query. Because if I like pop music, I bring pop artists into the conversation. If you talk about me, maybe you'll talk about Beyonce or The Weeknd or something, right? That's the key. Whereas if you make pop music, that pulls you into other conversations, right? Like if somebody likes pop music and Taylor Swift makes pop music, she gets pulled into all over the conversations. And so what we want to do is not match the 1 and the 1 and the 0 and the 1. We want to match my key with her query. And that's how much I pull her, 1 times 1. That's the dot product. And then if we want to find out how much she pulls me, you want to match her key with my query. And then that's the 1 times 0, so I don't pull her into conversations. I'm going to finish off very, very quickly with the graphical explanation of this. We have two embeddings, the keys and the queries. The keys is like pop music, so I'm going to project everything to that green on top. And the queries is makes pop music, so I'm going to project everything to the orange. So when I bring everything down to the keys, then the embedding is one-dimensional. We both like pop music. That's a 1 and a 1. And for the queries, well, she makes pop music and I don't. So when we do this and flip it, she has a 1 for make pop music and I have a 0 for make pop music. And when you find out how much I pull her, well, you just take my key, her query, multiply them and get 1 times 1 equals 1. That's a strong pull. And you want to see how much she pulls me, you take her key, my query, and then multiply them and get 0. And so you get a sweet pull. So this is, oh, sorry, I went too fast. So this is it. This is the attention and multi-head attention, but I like to see them, as words flying around, getting attracted, and transforming these embeddings so that they work better. And with that, I leave you because I think I'm about time. So thank you very much. Check out my YouTube channel, Serrano.Academy. Subscribe. I have a lot of explanations like this.
All right, thank you, Louis. Any questions?
Question over there?
Do we have a mic runner to run? Okay, there we go. Thank you for improvising.
Hi, very good analogies for all this complicated concept.
Thank you.
I wonder, do you have an analogy for hallucination?
Ooh, it's some like weird, some psychedelic. No, I mean, I think of hallucination as like it happens all the time. Like people say the models work well and sometimes hallucinate. I think they always hallucinate. They just sometimes hallucinate the truth accidentally. But I like to think of this as muscle memory, right? Like the model doesn't know facts or what to say next. It just has muscle memory. Like it reacts to things the way we react to things. So if you give it some words, it just like the muscle memory makes it react to give you a next word, and then so on. So I think of generation as muscle memory. And you can see this when you like train a model and you change some fact. The model keeps saying the old fact, the same way that we can't change our muscle memory that quickly, right? So I like to think about it that way. I don't know if it's...
All right, any other questions? I do have one of my own.
Sure.
Have you ever considered a career in marriage counseling?
Marriage counseling. I don't know. I would probably be the worst.
All right, well,
Your
thank you.
dot product is not that big. You guys are screwed.